morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I will be starting the third unit or the module 3 of Engineering Chemistry, and this module 3 it comprises of electrochemistry, that is the Nernst equation and its application, and relation of EMF with thermodynamic functions like enthalpy, delta F and entropy. Then in module 3 we have batteries, particularly lead storage battery. The next topic that I am going to cover is corrosion, its causes, effects and its prevention. And the last topic is phase rule and its application to water system. So today I will be starting with electrochemistry. Now, first coming to the electrode convention. The electrode at which oxidation is occurring is called the anode, and the one where reduction will take place is called the cathode. And in the cell, we write the anode on the left and the cathode on the right. A cell operating spontaneously in this configuration is said to have a positive total cell potential. When connecting it with the voltmeter, we connect the positive terminal to the positive electrode. If it reads a positive potential, then we have correctly identified all the terminals, and if we are getting a negative potential, then we must change and arrange or the add up or hooked up in the backward direction. So we have to reverse our assignment of anode and cathode. In a galvanic cell, the cathode is positive, because here a redox reaction is taking place for the production of electricity, and the electrons they move from anode to the cathode, so it is positive. Whereas in the electrolytic cell, the cathode is negative, because we are supplying energy from the external source. Therefore, the cathode is negative in the electrolytic cell. Now, coming to the galvanic cells, which are also known as voltaic cells. So, galvanic cell, they produce electric current by a redox reaction, and a typical galvanic cell is Daniell cell. So, here I have taken the example of a Daniell cell. Now, this cell, it uses spontaneous chemical reaction to generate electrical energy in the form of an electrical current. So, here I have two electrodes, one zinc electrode and the other one is the copper electrode. Here my zinc electrode is anode, whereas the copper electrode is cathode. So, in the case of galvanic cells, the cathode is positive, and the two half cells, this zinc electrode, it is dipped inside the solution of zinc sulphate, and the copper electrode is dipped inside the solution of copper sulphate, and these two half cells, they are connected via salt bridge. So, the electrons, they move from the zinc electrode towards the cathode. So, most of the batteries, they are made from voltaic cells. Now, in this case, since in the electrochemical series zinc comes above copper, therefore, zinc has a tendency to undergo oxidation. So, here the zinc ions, they come out from the electrode and they move to the solution, and the electrons, free electrons produced, they travel from zinc electrode to the copper electrode, whereas the copper ions from the solution, they get deposited at the electrode. So, the reduction of copper takes place and oxidation of zinc takes place. And this salt bridge, it completes the circuit. It does not lead to the accumulation of charges in the two half cells. Now, here you can see what I have explained. It is made up of two half cells. Oxidation, which is the loss of electrons, it is taking place at the negative anode, and the reduction, which is gain of electrons, it takes place at the positive cathode. Now, this salt bridge is to complete the circuit by joining the two half cells together. Now, in the above example, the different reactions which are going to take place. Here at the anode, the zinc is going to lose the electrons and get converted into the zinc ion. So, Zn plus 2 is going to be formed and it will release 2 electrons. Whereas, at the cathode, the copper ions, they are going to accept the electrons and get converted into copper. So, the cell can be represented as zinc solid, zinc ions which are being produced separated by a salt bridge, then copper ions and the copper solid. Now, the cell potential. The cell potential, capital E, it is the measure of how well a cell reaction can push and pull electrons through a circuit. What is the flow of the electrons? The electrical energy generated by a spontaneous reaction is proportional to the cell potential. The standard cell potential, which is represented as E naught cell, the standard cell potential, it is the cell potential measured when all the species are in their standard states, that is at 1 atmospheric pressure and 25 degrees centigrade, and it is given by E naught cell is equal to E naught cathode minus E naught anode. Now, next is the Standard Hydrogen Electrode. We can measure the difference in the cell potential, but for finding out the potential of the half cell, we have to connect it to an electrode whose potential we have fixed as 0, and that electrode is the Standard Hydrogen Electrode or the normal hydrogen electrode. Now, the convention is to select a particular electrode and assign its standard reduction potential the value of 0 volts, and this electrode is the Standard Hydrogen Electrode. Now, here in the Standard Hydrogen Electrode, it is made up of platinum. The Standard Hydrogen Electrode is made up of platinum coated with platinum black to increase the surface area. And this electrode is dipped inside a solution of 1 molar concentration of H plus ions, and hydrogen gas at 1 atmospheric pressure is continuously flowing through it, and the reaction that is taking place is a reversible reaction. This reaction is reversible in nature. Here I have taken the reduction reaction, but it is reversible reaction. 2H plus are accepting the electrons to get converted into hydrogen gas. The standard aspect to this cell is that the activity of hydrogen gas and that of the H plus aqueous, they are both 1. This means that the pressure of H2 is 1 atmosphere and the concentration of H plus is 1 molar, given that these are our standard reference states. Now, standard as a reference, how it works as a reference. Now, once we have chosen standard hydrogen electrode as a reference, this reference cell is employed as one half cell with all other cells. We connected with the other half cells. Since its potential is assigned the value of 0 volts, so all of the potential difference measured experimentally, it is attributed to the other one, that is the test electrode, whichever electrode we are connecting with the standard hydrogen electrode. Since now we are cataloging the reduction potentials, these cells are formed by connecting the standard hydrogen electrode as anode and the other half cells as the cathode. So, here I have connected my standard hydrogen electrode with the copper electrode. So, here this is the representation from my standard hydrogen electrode, then a salt bridge, then the copper electrode. So, my standard hydrogen electrode, it is undergoing oxidation, therefore, it is written on the left hand side, whereas the tested electrode, it is at the right hand side, it is working as the cathode. So, here reduction of copper is taking place and the measured potential in this case comes out to be plus 0.340 volts. Now, since all this activity of all the components on the copper cell are standard, therefore, 0.340 volt is the standard reduction potential of the copper cell, half cell. Now, we can take another example. The another example is of the zinc half cell. So, I have again connected my zinc half cell to the standard hydrogen electrode, and in this case the measured cell potential, it comes out to be minus 0.7626 volts. So, this is the standard reduction potential for my zinc half cell. Now, coming to the calculation for cell potential, because we tabulate the reduction potentials, therefore, the cell potentials is calculated as, we calculated as E cell is equal to E cathode minus E anode, where capital E is the electrode potential. Here the minus sign which is present only because we are using reduction potential table, and by definition an anode is one where oxidation takes place. Now, here I have tabulated the standard potentials of some of the half cells. Now, more negative, here we can see the reduction potentials. The more negative is the standard electrode potential, it has a more tendency towards oxidation, and more positive is the reduction potential, it has more tendency towards the reduction. So, in this table, the elements which are present above hydrogen, they have more tendency towards reduction, whereas here the other elements which are present on the negative side of the hydrogen, they have more tendency towards the oxidation. Now, higher in the table means they are more likely to act in a reducing manner. Now, F2 is a stronger oxidant than Ag plus, because F2 was at the top and Ag comes below. Similarly, copper is a weaker oxidant than cerium. Now, lower in the table means a greater tendency to be oxidized, that is, it is a reducing agent or reductant. It itself gets oxidized while reducing the other one. Now silver is a strong reductant than gold. Similarly, cobalt is a weaker reductant than tin. Now, how do we use the table? Now, I am showing choose one reaction for reduction. So, I have chosen one reaction for reduction, that is gold. It accepts the electron to get converted into Au, and the electrode potential is plus 1.69. Now, I have to choose another reaction for oxidation. So, I have chosen another reaction, that is copper plus 2 electrons. It accepts the electrons to get converted into copper, and the potential is plus 0.34 volts. Now, here gold, it undergoes reduction, and the copper electrode, it undergoes oxidation. So, when it is undergoing oxidation, this reaction is going to get reversed. So, my copper will be producing Cu2 plus 2 electrons, and when the reaction is getting reversed, the sign of my electrode potential will also get reversed. So, the overall reaction, by the adding up the reduction and the oxidation reaction, my overall reaction becomes 2Au plus Cu gives you Cu2 plus 2Au, and the cell potential is equal to plus 1.69 minus 0.34, for it was positive for the reduction reaction, but since we are using the reaction for oxidation now, so my half cell potential, the sign should be reversed. Therefore, it is minus 0.34 volts. So, E cell is equal to E cathode minus E anode, and the resulting will be plus 1.35 volts. Now, again I have taken another example. Similarly, I have taken one reaction for the reduction and the other reaction for the oxidation. This is the overall reaction. Here comes the overall reaction, and this is how the cell potential has been calculated. So, this is the reduction reaction having the value of plus 0.15 volts at the half cell electrode potential. This is the oxidation reaction having 1.61 value. So, it will get reversed when we are going to use it in the oxidation. This was plus 1.61 for the reduction reaction. For oxidation reaction, the sign will get reversed. So, the cell potential will come out to be E is equal to 0.15 minus 1.61, which is equal to minus 1.46 volts. Now, the more negative the reduction potential is, the more readily the element acts as a reducing agent, that is, it itself gets oxidized. Higher is the negative reduction potential, that element has a tendency for self oxidation, and it will undergo self oxidation and will reduce the other one. Reduction occurs at the electrode with higher potential, and oxidation occurs at the electrode with lower potential. The unit of potential is the volt, and unit of charge is the coulombs. So, and they are related by 1 volt is equal to 1 joule per coulomb. The charge of 1 mole of electrons is given by Faraday constant, and for Faraday constant we take it as 96,500 coulombs per mole. Now, we can combine the standard cell potential and Faraday's constant to give us an equation for delta G naught. This is the standard Gibbs free energy change. So, delta G naught will be equal to minus NF E naught cell. So, where delta G naught is the change in Gibbs free energy, N is the number of moles of electrons, and F is the Faraday constant, E naught is the standard cell potential. So, change in the standard Gibbs free energy is given by minus NF E naught. Or you can say, now this has been given by Nernst, that the change in the Gibbs free energy, it depends upon the electrode, the type of electrode we are using, the concentration of the cell, and also on the temperature. I will take in the next slide. Now we have a relationship between Gibbs free energy and equilibrium constant. Delta G naught is equal to minus RT ln K, where capital K is the equilibrium constant. And delta G for a reaction, it depends on the concentration by the equation delta G is equal to delta G naught plus RT ln K, where RT ln Q, where Q is the reaction quotient and it is given by the concentration of the products divided by concentration of the reactants. But we also know that delta G is equal to minus NFE cell, that is the work done by the cell, and delta G naught is equal to minus NFE naught. So, on putting these values of delta G and delta G naught in this equation, we get minus NFE cell is equal to minus NFE naught cell plus RT ln Q, and dividing the entire equation by NF, we are going to get E cell is equal to E naught cell minus RT upon NF ln Q. Again, Q is nothing but concentration of the products divided by concentration of the reactant, and this equation is known as the Nernst equation. And we can derive that the cell potential at any condition depends on the potential under standard state conditions and a term for the potential at non-standard state conditions. Now, we are going to take an example. In the first, I am taking that here the iron is undergoing reduction and vanadium is again undergoing reduction. Now, these are these half cell potentials. To get a final positive cell reaction, the more negative half cell, it must act as a anode. Otherwise, we are going to get the answer in the minus, and that shows that the cell will not exist. So, to get a final positive cell potential, the more negative half cell, it must act as the anode. So, here the equation becomes iron undergoes reduction, whereas vanadium it undergoes oxidation. So, the E cell, it comes out to be plus 0.75 volts. Same we have taken the example with tin and silver. The more negative potential reaction is the anode. We are going to balance out, multiply the silver reaction by 2. So, here the overall cell E cell will come out to be plus 0.94 volts. This is how we calculate the E cell. Now, next, coming to the applications of Nernst equation. The Nernst equation, it can be used to calculate the single electrode reduction or oxidation potential at any condition, that is standard conditions and non-standard conditions. We can calculate the standard electrode potentials. We can compare the relative ability as a reductive or oxidative agent. It is used for finding the feasibility of a combination of such single electrodes to produce electric potential. EMF of an electrochemical cell can be known. We can also find out the unknown ionic concentrations. We can also calculate the pH of solutions and solubility of sparingly soluble salts with the help of the Nernst equation. So, these are the various applications of Nernst equation. Now, I am taking one numerical here. The question is, the standard electrode potential of zinc ions is plus 0.76 volts. What will be the potential of a 2 molar solution at 300 Kelvin? Now, the Nernst equation for a given condition, it can be written as E Mn plus by M is equal to E naught minus 2.303 RT upon NF log 1 by Mn plus. So, here E naught is 0.76 volts, number of electrons involved will be 2, Faraday will be 96,500 coulombs per mole, metal ion concentration is 2 mole, R is 8.314 joule per Kelvin per mole and temperature is 300 Kelvin. Now, we are going to substitute all these values in the Nernst equation. So, we are going to get E Zn plus 2 zinc will be 0.76 minus 2.303 into 8.314 into 300 divided by 2 into 96,500 into log 1 by 2. And after calculation, I will get the value of 0.769 volts. Therefore, the potential of a 2 molar solution at 300 Kelvin will come out to be 0.769 volts. Another example, what is the cell potential of the electrochemical cell in which the cell reaction, we have given the cell reaction, and in the cell reaction we can see the lead is accepting the electrons and it is undergoing reduction, whereas cadmium, it is releasing the electrons and it is undergoing oxidation. And we have been given that E naught cell is equal to 0.77 volts and the temperature is 25 degrees centigrade, concentration of cadmium ion is 0.02 molar and lead ion is of 0.2 molar. Now, since the temperature is 25 degrees centigrade, so we can reduce the Nernst equation to E cell is equal to E naught cell minus 0.0592 divided by number of electrons log 10 Q. Here the 2 moles of electrons, they are transferred in the reaction. Therefore, number of electrons will be 2. the reaction quotient, it is given by, now since cadmium ions, they are being formed in the products and lead ions, they were present in the reactants. So, Q will be given by concentration of products by concentration of reactants. Therefore, it is taken as concentration of cadmium ions divided by concentration of lead ions, because lead ions, they were present as reactants, and after accepting the electrons, they are undergoing reduction. And the concentration of cadmium ions is 0.02 molar, whereas of lead ions is 0.2 moles. So, by putting all these values, we are going to get that the E cell is equal to 0.3066 volts. So, the cell potential of this electrochemical cell at 25 degrees centigrade comes out to be 0.3066 volts. Another example, the copper ion concentration in a copper silver electrochemical cell is 0.1 molar. If E naught of reduction Ag plus to Ag is 0.8 volts and E naught for copper, that is again reduction potential, copper plus 2 to copper is 0.34 volts, and cell potential at 25 degrees centigrade is 0.422 volts. Find the silver ion concentration. So, here we can find out the E naught cell by putting these values. E naught cell is given by E naught cathode minus E naught anode, and cathode is silver whereas anode is copper. So, 0.8 volts minus 0.34 volts, which comes out to be 0.46 volts. Now, since the charge on the copper ion is plus 2 and the charge on the silver ion is plus 1, therefore, the balance equation or the balance cell reaction will be 2Ag plus copper will give you 2Ag plus copper 2 plus. Now, the 2 electrons, they are transferred in this cell reaction. Therefore, the value of N will be taken as 2. Now, the Nernst equation for this electrochemical cell, it can be written as E cell is equal to E naught cell minus 0.0592 divided by 2, which is the number of electrons, log 0.1 by concentration of Ag plus to the power 2. Why 2? Because here in the balance equation it is 2 Ag plus, therefore, Ag plus to the power 2, square of the concentration. Therefore, now minus 2 log Ag plus will be 2.283, or value of log Ag plus is minus 1.141, and after taking the anti-log, the concentration of Ag plus, it comes out to be 0.0722 molar. So, here we have calculated the concentration of one of the ionic species. Thank you.